What's the minimum requirements for a circuit, an electrical circuit? We have a power source, right? Well, what's the minimum? You gotta have a load. Yeah, we gotta have at least 2 conductors. Right? Okay, this is the minimum requirement for. So over here, if I come over here and do this, if I put a push button right here, and then I come over here and do that, what's missing? And we call this short circuit, right? You understand that? Because there's no load. This is happening sometimes in this class right here. This is one of the basic things that we should know. Another thing that I've noticed is y'all having problems with making drawings according to industry standard. Industry standard requires you, when you draw them, to put those dots right there, right? And why? So if we don't have a dot, so we're having to do some things like this, where we was coming over here doing this, and then we had a ceiling, then we had a sensor, and then a ceiling circuit around there, and then we're having to make a tap right here. Well, and the way it was drawn, I can't remember, but we had a line coming down, and this line right here had to come over and cross the line right there. And I know this is not connected because there's what? There's no dots. So that's why these dots are very important. Unfortunately, when they came out with the PLC programs where you draw ladder logic, what don't they put? They don't put the dots. Okay. That makes sense. And we cross lines and those things also, but they don't put dots to indicate a connection or not a connection, which on a PLC gets kind of confusing sometimes. What's the normal requirement for a circuit? What do circuits normally have? Of course, they all have these, right? We gotta have a source for power, or a voltage source in our situation. We gotta have a load, and we gotta have 2 conductors, right? At least 2. Depends on what type of circuit it is. We're talking about the minimum requirements. And what's the 4th requirement for a normal circuit? A control device. Yeah, yeah, we don't need a ground. I mean, all we need is that we need what we refer to as a common. Yeah. But that's if it's only a one element circuit, then common is a relative term, right? You understand? Yeah. In other words, if I come over here and do this, what's the common? No. It's whatever you establish as a common, right? You understand? So this circuit right here really doesn't have a common until we decide what the common is, right? You understand? And we add that symbol. Relay, you could choose which one common. Yeah, and of course in PLCs we refer to it as syncing or sourcing. Yeah. And of course normally what we do, now normally what you said was probably right, because normally when we draw a schematic, okay, y'all listen to this, then this is what in electricians refer to as the hot side, because it's drawn on top, right? You understand? And normally the common is drawn on the bottom. Right, you understand that? Yeah. Yeah. I don't know what you mean.
90 degrees.
Well, 90 degrees, we normally don't really draw it like that. Yeah. Oh, I know what you mean. If we turn it like this, if we draw it like this. Yeah, when we draw it like this, this in electricians, they would refer to this as the hot side. In electricians, refer to this as the neutral. Now, normally neutral, when we use the term neutral, what does that mean? Well, no, neutral is a current connect. It's not ground. It is a current carrying conductor that's referenced to ground. So in electricity, we have three wires. We have what they refer to as a hot, and then we have what we call a neutral. And right here we have a ground. Now, what's the difference between the neutral and the ground? If I came back here in my panel box, I would see these two are connected together and they're connected to earth ground. Yeah, ground is only supposed to carry current when things go wrong. So NEC, National Electrical Code, if y'all taking it, they don't call them neutral and they don't call them hot. They call this the ungrounded current carrying conductor. Ungrounded current carrying conductor. And they call this the what? They call this the grounded current conductor. And they do that so you don't get that confused. So when we reference stage ground, so ground's in there for what? It's got one purpose in life.
So carry the both.
Safety.
Things go wrong.
It prevents anything because it prevents anything that's metal from becoming electrically hot. Because if somehow this gets in contact with this, then you're gonna blow your brain. So if we run ground to our metal devices, all our metal devices, then there's no way in the world, if it's wired correctly, that metal device can become electrically hot. That makes sense? You understand? So yeah, so we're not doing this. We don't have a neutral. We have a L1 is considered the hot side and L2 is considered the common side. Because ground does not come through the transformer. Y'all understand that? So you literally have to ground the secondary transformer. So that's why your house has a watt on it. It has a ground over there by your box, because they ground this guy. I'm sorry. They ground the neutral and the transformer. So if you go out to your transformer, it's up on a pole, you'll see a wire coming down, driven into a ground, right? Understand? In your house is referenced. So that way your house, any appliance inside your house cannot become electrically hot. Now we do have what's called double insulated devices, so you got a drill and it's made out of plastic. The plastic is an insulator, right? You understand? So that way you'll see these devices not have a ground conductor, because plastic cannot become electric. So this is the basic requirements of a normal circuit. This is the minimum requirements for all circuits. And like I said, some of y'all are trying to leave off the load. You are literally connecting through a push button. You're connecting L1 to L2. That's what we call a short circuit. Yeah, we try to teach there's a difference between a short and a short circuit. And what's the other requirements? First of all, in diagrams that's drawn correctly, whether they're schematics or not, if they're schematics or they're line diagrams, we have no crooked lines. They're all straight. So all turns are made at 90 degrees, right? You understand? So I'm seeing some of this too. So I come over here and you'll put a push button and you come over here and do that. Well, that's illegal. You come over and you put your little dot there and you do that line, but that's illegal in motor controls. And what you're trying to do is you're trying to make a diagram that not you understand, right? But everybody understands, right? You understand. So dots are very, very important. And like I said, unfortunately in PLCs do not put dots at connection points. How many loads per line? One load per line. You gotta, I should say the maximum, but I should also say the minimum, right? You understand? Well, that's not true. One load per rung, but you cannot have a path from what? So every rung's got to have a minimum of how many loads? One. How many loads per line?
One.
Maximum of one. How many loads per rung? Many. How many control devices per line? Many. How many control devices per rung? Many. Yeah. So when we talk about a series circuit and we talk about a parallel circuit, it has nothing to do with the control device. That does not determine a parallel circuit.
Control devices carry a load.
Huh?
They carry a load.
What's that?
Some control device. I mean, like, now, even like, oh, no, they don't, but they go to.
Well, yeah, control devices can carry a load. In fact, a lot of control devices do. In motor controls, all your control devices carried a load, right? The current of the load fed through the device. And this is also true on a solid state. The current that runs a load has to go through the device, right? You understand? The problem is a lot of our solid state sensors have to be powered up. And this might be what's giving people problems. Of course, a solid state control device, normally what we do in motor controls is we put it inside a diamond shape. So if I see a diamond shape, it means it's what? Solid state. Right, you understand? Now in PLCs, it gets a little more complicated in that they identify what type of control device it is. And then I come up here and then I put a contact. We usually draw it as a limit switch inside of it. And then over here, the load is going to be right here. What type of load could it be? Could be a light or could be a relay. And we use, and this book calls this an interface device. So that's what our labs call that, interface device, which is good. So interface means you make a connection too. I don't know where that line just popped up from. So the problem is with most of our solid state sensors, most of your solid state sensors only have one contact. And if you have one that has more than one contact, that's the exception, not the norm. Now, some solid state sensors can power up through the circuit. So, you know, if this is 1K and this right here is, 200K, there's current flow through the solid state sensor. It's just that it's so small, we could, in fact, y'all measure that. So the inductive sensor that we're using is powers up through this load right here. Okay, y'all understand that? Some require too much current, like our photoelectric sensor and our temperature sensors. So what do we have to do there? Yeah, we have to put a power lead. This is still the minimum requirements of a circuit, right? You understand that? Because here we still have, it considers this to be the load for that circuit. And still the main current load that runs our intended control load, so this is the intended control load right here, still goes through the solid state relay. It's just that what happens now, in fact, we don't call these solid state relays anymore, we call them photoelectric sensors. So normally the term, when they say solid state relay, they're talking about either a capacitive sensor or an inductive sensor. And capacitive sensors and inductive sensors require so little current, they can power up through the load of the rung. But your temperature sensors, your photoelectric sensors, our pressure sensors, those have to be powered. right? You understand? Yes or no? So this is a little bit different. Now what we have on these solid state sensors, especially if we have what we call a 3-wire sensor or we have a 4-wire sensor. Anybody know the difference?
3 wires, power, 4 wires for,
Well, 3 wires, one of them, so 3-wire sensors, two of them, can't say that, 2 of them required for power, and then one's required for the run load, right? Okay, so what would a 4-wire sensor? So this is the problem we have. The temperature sensor that we have is a 4-wire sensor. In fact, if you take it and look at it where the sensor feeds into the little circuit board, you'll see 4 wires.
one for heat.
Huh?
For communication, or for,
Two of them, well, one of them's for power.
then you said 2 were for power.
Well, yes, but this guy here is shared. So this guy here is shared by the what? The load. So this wire right here is the additional wire that's required by power. Okay. So we got 2 signal wires. So they call this the signal wires. Now what those are, and we figured this out by the way, when I took it apart and looked, is literally that temperature sensor has this. I'm gonna make this bigger so I can draw it so y'all can understand it. And this is what gets kind of confusing. Is this a 4-wire sensor? And what was going on is we were wondering why we had 2 relays on it. Y'all understand? So the way this guy here works, it's this guy right here.
Oh, the double throw.
Yeah, it's a single pole double throw. And the way this works is this comes out of this. So this is the way our temperature sensor works.
So what do you do when you open?
And then we have 2 relays, which we'll call R1 and R2. Relay 1 and relay 2. And then of course we got the 4th lead, which is the what? Power lead. So we got to figure out which one we need to use. Normally we want to use the one that is normally open, because if we use the one that's normally open, then the temperature label set will cause it to energize. The one that is called reset is de-energized. So this guy would operate opposite of the way we want it to work. This guy right here would operate in direct. So as soon as you apply power, one of those relays are going to, whichever one that energizes, that is not the one you want to use. Don't understand that? And how can you tell? Well, you can get an ohmmeter and put it across between common and normally open. And if it measures, this is before you put power on that side. If it measures 0 ohms, that's the one you don't want to use. Yeah, you understand? Yeah, everybody understand? Now I think the way it's been working out, I've already done it. I think the one on the right is the one we want to use, right? I think. Yeah, the 2 relays. I think the one on the right is one you want to use. But you can do that real easy. Power up. Now make sure with your ohmmeter you got power on that, and you don't want to put power into a circuit. So make sure you don't put your ohmmeter in here. What you're going to do is you're going to hook it up to the contacts, and the contacts right now are not wired up to anything, right? You understand? And what can you do down here? Since these are not powered yet, what can you do? Or I believe, in fact, I think you don't even need to power it up because the normally closed is going to be normally closed even when there's not power applied. So I believe before you even power it up, you can find which one is this guy and which one's that guy. Okay, you understand? Yeah, so when the thing's not powered up, those relays are going to be in a I gotta think about that. I think both of them will be this way. Because neither one of them's energized. So they don't change states until you put power on it. So you can't do that. It's gonna have to be power. Now these guys here,
But they also be, standard. When you find one.
well, the other one's gotta be the same, but what I was thinking is that you could do it before you power it up, and then I reneged on that. Because both of them will be de-energized, and if both of them de-energized, both of the normally closed will be closed, and both of the normally open will be open. So to find out which one we want to use. But it's not any big deal, so if you wire it up, and if it operates opposite of what you want to operate, then you need to move over to the other relay. Okay, you know what I'm saying? But I'm almost sure the one on the right is the one that you want to use. Let's do this backwards. So a 3-wire sensor is going to have 3 color wires on it. It's going to have brown, black, and blue. Are we okay? And of course, it depends on whether the black wire is always the one. No, what's so strange? So we get in DC normally we get used to saying black is negative and red is positive. On sensors they didn't do it that way. So black is your signal wire. Brown and blue are your power wires. Now this is a PNP sensor, which means it does what? It sources. So that's why they got the signal wire label 12. So, right?
Syncing.
Yeah, so the PLC would be syncing the sensor source. Now y'all understand that? That's enough. So this is good too. So this is a PNP sensor. That's a 2-wire sensor. That's wired the same. That's not right. That's not right. Okay, these this would be a what? So here's my load. Here's common over here. So this would be your PLC. So your PLC is syncing. So this would be, I'm sorry, your PLC is syncing. So your sensor has to work. That's what I'm looking for. Every one of them so far has been PNPs. And then we'll look at the color code for a, okay, so here's an NPN. Now notice, the blue is what? Negative. So the blue is negative. The brown is positive. So you'll understand that. And the black is always what? Signal. Now we're asking what the 3 wires do. Oh. So the brown wire is positive. The blue wire is what? Negative. And the black wire is the signal wire. Y'all understand? Over here, the brown wire is positive. The blue wire is negative. And the black wire is the signal wire. Now what changes is the way we look it up, right? You understand? So here, the load is hooked to ground, So this guy here is sourcing, right? You understand? Here the load is the power, so this guy would be syncing. This is the PNP sensor. That's something you have to know. The way you hook the sensor up is the same. I'm sorry, as far as the wiring is the same. What's that? Brown is plus, blue is minus, black is signal. Okay, y'all understand that? It depends on how you hook the load up to a sensor. So if you get an NPN sensor, and by the way, so what we're saying is that they don't say a syncing sensor or a sourcing sensor as far as I know. When you buy them, they're either what, PNP or NPN. Okay, so let's look up a four wire sensor color code.
Oh, I got it.
That's differential pressure. No, that's not. So this is a 3-wire sensor, right? This is a 3-wire sensor. It's hard to see, right? It's hard to see too. These are not really sensors, those are heaters. That's a heater too. That just gives us the colors. So these are the colors we're dealing with here, right? Can y'all see them? Green.
Colorblind. Well, the water's colorblind, isn't there?
We're probably gonna have to look this up a little. Somebody go back here and get me one of those temperature sensors. Huh. Oh, wrong class. I get y'all in troubleshooting mixed up all the time for obvious reasons. Huh? Well, a lot of y'all are in the same 2 classes.
I learned how to draw those,
The common sense way to buy. TSD 250. TSD 250. I can see it. How much that thing cost to fix?
Just that little.
Yeah, just the sensor.
That's the brain.
Maybe we should make this thing a little bit more efficient so that you don't pull it out.
What we're doing is looking for the wiring. It looks like it, so here we go. Can y'all see it? For this one. I need to save this. So here, one is power, right? So that's brown. That's the same as the other, right? Blue is white. Brown. So that's the same as the other set. The black. So what color do they have? White. A white's your other output of your centerfold plus plug. Yeah, that wasn't right. That wasn't right. So that's why I decided to look this up. I'm gonna save this and put it up on the blackboard. Or what I need to do for this class is get all these modules and get all the part numbers off all these devices and go out and get the data sheet off the devices that we're using. On this one, they're keeping the exact same color code as the 3-wire sensor, except they've added a white. And if you look at the top of the relay assembly, I don't have my camera turned on. I didn't think I had it plugged up. But if you look right in here, you'll be able to see it where it comes in and actually connects to the relay. So, if y'all had a chance to look at the test review. It's been up for a while. I think I sent y'all email, right? Because we have a test when? At the, yeah, not Monday. At the what? It's test 3. Wouldn't we give test 3? It's already class. We don't give it at the end of class. It will be time. If you come in late, you're not going to get extra time to complete it. As the time runs out, you're going to have to submit. We're going to be, we'll be back over in the, at the hall building.
Test 3 is exactly next.
Today's the last day for labs over here. Tuesday, we'll do a lab over on the manufacturing line. And basically what we'll do on both the lines is we're gonna move around and find every sensor on every module. So it's not really a difficult lab. And then, of course, describe the function of what that sensor does. That's what we'll be doing Tuesday after the test. And then that will be the absolute last day to do a lab. Okay, y'all understand that? But today is the last day to do labs where? Over here. Everybody understand that? So we won't be back over here. And then next Thursday, we have the final exam.
Okay. We're gonna do this Thursday.
What's that?
Say leaving, I mean, question we can have,
Leaving.
say leaving the lab.
No, the labs are, today is the last day to do labs over here.
Okay.
So we're gonna do it Thursday.
Yeah, I think it's.
Oh, I'm sorry, I'm sorry. Yeah, we'll be back over here, we'll be here Thursday. I got my brain on next week. I forgot this is the first day, so we'll be back over here. So today's not the last day to do labs. Thursday is the last day to do labs. Huh?
No, this Thursday.
Next Thursday is the final. Yeah, the last day to turn labs in is the day of the final.
Next Monday is final for trouble.
Yeah, Monday is the final for troubleshooting. If you remember, we had to extend,
Tomorrow we have.
yeah, tomorrow we have a test in troubleshooting. And then we have the final for troubleshooting on Monday.
Hammering stuff out.
Because we lost two classes in Tuesday, Thursday. So that's why we go Tuesday, Thursday next week. But the Monday, Wednesday class, we only lost one class.
It worked out ridiculous, so we'll have what about eight?
Y'all still having all y'all's finals next week though, right? All y'all's, yeah. Yeah, you're in our program, We, and I think we explained you that we do our summer term in 8-week terms, right? Y'all understand why? Yeah, and plus we don't have to change the way we teach class. So, and then it gives us those 2 weeks, and it's worked out this last 2 years that we've needed them because last summer, if y'all remember, we went to Tennessee to get the level 1 certification. And then this year, huh? Test reviews, test 3. So anything on test 3 we need, oh, it's not available. Let's see there. Y'all said, yeah. And I said,
Wait,
I think I'll add a little bit, well, no, some of the stuff y'all should know, right? And like I said, some of y'all's having the problem with the minimum requirements for a circuit, and some of y'all are drawing your circuits and having short circuits. And, that's not good.
Push the button.
Well, luckily
I
y'all,
like sparks flying when I press the button. Don't forward, right? I like it when sparks fly when I press the button.
I don't.
Do what?
Okay, so interface, y'all know what that is?
Say what?
Interface.
Interface.
In these labs, what interface?
Interface is the,
Yeah, usually in here it say device, and what do we use those interfaces for?
Control heavier load.
Heavier loads plus. Two uses. I know it's got 3 uses.
I know somebody if like.
So these interfaces have three uses. Thomas came up with one, allows us to have a heavier current load, right? Is probably what you're talking about.
Yeah. If like Well.
Well, that's 5, you're right. So what happens, it also protects the sensor. So if you have and so, you know, you got a little relay that costs $25, you got a sensor that costs $90, you know, your little relay could burn it up and still save that $100 sensor, right?
Yeah.
Well, these solid state sensors are not cheap.
One
So we
thing-
protect them. It protects us a bit against, short circuits and everything.
One thing that I've learned from Revere is that we're able to use the relay to control AC and DC. So,
Well, and yeah, and it allows you to change the type of it allows you to go to a different voltage. So this sensor works off 24 volts. So that's why we got to plug it into this guy right here. But we're controlling 120 volts. Well, how can a 24 volt sensor control 120 volts? With an interface. Okay, or a control relay, right? Okay, so it allows us to change the type of voltage and also the quantity of voltage. So instead of, this is AC, I'm not sure, it might be a DC sensor. In fact, I think it is. Okay, that's a DC power supply. Well, we're going from DC over to AC, and not only we're going from DC over to AC, we're going from 24 volts DC over to 120 volts AC, right? And what's the next one? So protection, good. So it allows us to protect our sensor. It allows us to change the amount of current because what we call operating current. So the operating current to control the relay won't be near as much as the operating current required to run the load, right? The true load. So there's no way in the world that sensor could turn on that 3-phase motor like that. And sometimes we actually go through stages. This relay right here this little guy right here could not control the 3-phase motor.
So, but you can connect that to a contactor.
We can connect it up to a contactor. So this guy probably don't have enough current to pull into the contactor, right? You understand? But this guy right here does. So that's very popular too. You actually use relays to get control a higher level of current too, which is what. What's the next one?
Wait, wasn't that three?
No, we got quite a few. I think we came up with 5 so far. How many contacts does a solid state sensor have?
It provides more contact.
Yeah, it provides more contact. So that interface devices has all those features. So what are those features? It allows us to control a higher level of current, right? You understand? It allows us to change the type of voltage and the quantity or amplitude of voltage. It provides protection for our very expensive sensor, right? In other words, we can sacrifice the interface device instead of the sensor, and it allows us to add more contact. Okay, we okay?
Yeah.
Deadband. What's the deadband?
Just state whether the device is on or off.
Yeah, so it's a state between on and off. Right, you understand that? So all compressors have a deadband. Your air conditioning unit has a deadband. If you set your things for 71 degrees and your HVAC tried to maintain exactly 71 degrees, it would be constantly cycling, right? All the time. So there's a deadband, sump pumps, there's deadbands built into a lot of these devices to keep them, they compensate for trying to regulate perfectly, right? You understand that? This is the big problem we have with proportional control. It tries to regulate perfectly, so what happens is, especially something that's got inertia, it ends up surging. So the motor needs speed, it adds speed. The motor overshoots, it needs to slow down. Slows it down, it undershoots. So this is why proportional control is basically prone to oscillation. And that's why we had the integral control. And basically integral control gets rid of the oscillation caused by proportional control, but it adds time, and then differential control sets the speed, right? You understand that?
So you're basically saying, you're setting a parameter, you're setting so that's dead band. So just say
The dead band is basically going,
well, I mean, you basically set, some of those sensors you set yourself. You set that.
yeah, so the temperature sensor, we set the dead band, right, you understand? Digital sensors, we don't have to worry about it because they energize at a voltage. So they're either what, on or off, right? Unless we get around what we call the holding current.
I'm trying to think of what,
Deadband would be like a compressor. So you regulate your tool at what, 60 psi, and you set your compressor for 170, right? So what happens is it runs until it gets up to 100, and then it turns off. Then you run it off your tank until you get down to whatever the low end is. So compressors have, and what it does, that situation allows us to use what we call non-continuous motors, which these are motors that are not designed to run 24 hours a day, 7 days a week, so they're cheaper. So your compressor don't have a continuous duty motor on it, it's got an intermediate duty motor, and they just, I need to run a pop. So continuous duty motors are designed to run 24 hours a day, 7 days a week. Intermediate duty motors are used to control something that's got, basically, it's got a bend. So a sump pump would be an intermediate duty motor. A pool pump would be a continuous duty motor. Hysteresis is basically a drawing that represents when we have. So hysteresis is usually a difference between when it energizes and when it don't energize. Is the difference between when it energizes and when it de-energizes. So let's say a compressor, so I have it energized at 70 psi, and it de-energizes at, turns off at 60. So what it would do is it would come over here, and let's say this is 70. Well, what it would do, it would come over here and turn on at 70 and build up to what? And then what it would do, it'd turn off, but that pressure would stay up here, right? As long as we're not doing it. And then what would happen is it would start discharging. It discharges like this until it gets back down to 70, and it would do this. This right here is called the hysteresis. And this is what we call a hysteresis curve. So usually everything that's got a dead band generates what we call a hysteresis curve. That makes sense?
If you've got a normal compressor that's not made to work with continuous run, and you run it like a continuous,
Then you're decreasing the life expectancy of your motor. Motors are burning.
so it would only burn up, it wouldn't blow up.
Well, once you run off your, once you're running off your pump, then what's going to be affected is number one is your flow rate. Because normally your pump don't have the ability to keep up with the flow rate of the tank. Does that make sense?
Yeah.
And of course, most compressors, and another thing that happens is that you get pulsation in your, if you ever did spray painting, and you run out of tank and it starts running on your compressor, then your spray painter is gonna pulse. You're not gonna do it. Really good. So a lot of people that do really good spray painting, they use what they call continuous run compressors. where they use turbines and stuff like that, and they get exactly the same flow rate all the time.
Yeah, I just thought
Or
I'd
they buy
ask.
an extremely big, you wonder why they get these big old compressors that have them real big tanks,
We're rated in SCFM.
you know. Well, several rates, there's cubic feet, and it depends on whether you're at air pressure, where it's rated, I can't remember. One of them is rated from, sea level, and then other ones are rated at different altitudes. But that would be the flow rate of the compressor. But the problem is, if you run off your compressor, then normally, if it's a piston compressor, you're gonna get one. You're gonna get oscillation on it. Some situations that's not bad, but if you've ever did spray painting, that's critical. You wonder why these paint shops have these extremely big compressors, or they use what they call continuous flow compressors, which means they usually use a turbine that spins all the time and generates exactly the same flow rate and exactly the same pressure.
You guarantee service quality.
So yeah, you shouldn't run, and of course, all you're gonna do technically as far as your compressor goes is the life expansion of your motor's not gonna be. Here's the, so probably what that means is you need to buy a bigger compressor.
That's what I'm thinking, because I noticed that the, every year, whatever waiting forever, compressor is practically melting, the rubber pads and bottom is so hot. They're running all the time.
Or they can buy a continuous flow compressor. Continuous flow compressors are pretty expensive though, but over time they'll pay for themselves. So it sounds like in your situation, they probably need to buy a bigger tank with a different compressor. So y'all okay on hysteresis? What happened to my? Oh, y'all gonna take a break.